We'll now look at another method for evaluating limits, which is called the squeeze theorem. So essentially what the squeeze theorem says is we're going to suppose we have three functions. And in these three functions, we're going to suppose that f of x is smaller than g of x, which is smaller than h of x. This may not be true everywhere, but it needs to be true in some interval around our point x0. And we're going to further suppose that we know two of these three limits. So we know that the limit as x approaches x0 of f of x is equal to some known number L, and so is the limit of h of x. So we know f and h have the same limit at a particular point. Then we can conclude that our limit of g not only exists, but is also this exact same number. And this is called the squeeze theorem because essentially we have some function f, we have some function h, we know their limits are the same at some point, and we're squeezing g to be into the middle of them. So now that we have that, let's look at some examples. The limit as x approaches 0 of x squared sine of 1 over x. So we can't really directly evaluate this because we don't really know what 1 over 0 is. So let's think about this using our squeeze theorem. One thing we do know is that sine is always between -1 and 1. So in that case, this thing is between -x squared and positive x squared, because the sine of 1 over x has to be between the 1 and -1. Well, as x approaches 0, -x squared is going to approach 0, and x squared is going to approach 0. So this limit must be 0. Now let's look at the limit of sine of x over x. This one's a little bit trickier. However, we're going to assume that we know cosine of x is less than or equal to sine x over x, which is less than or equal to 1. And in fact, this is true. I'm not going to outright prove it here, but it is a known fact. Well, cosine of 0 is 0, and the limit as x approaches 0 of 1 is, or cosine of 0 is 1, sorry. The limit as x approaches 1 of 1, the limit as x approaches 0 of 1 is 1, so our squeeze theorem says that this limit has to be equal to 1. And this is a very fundamental limit in calculus. The limit of x goes to 0 of sine x over x equal to 1. So in our next couple of examples, we're going to demonstrate on exactly some different ways to use this. I want the limit as x approaches 0 of sine of 6x over 7x. In order to actually use my known theorem, what I can really say is that the limit as x approaches 0 of sine of ax over ax is 1. So as long as the number on the top is the same as the number on the bottom, we can conclude that this limit is 1. But that's not the case here, so we're going to rewrite it. I can't change an argument inside of a sine function, so that has to stay as 6x. So I'm going to need a 6x on the bottom. And in order to do that, I'm going to have some kind of balancing act. I wrote an extra 6 on the bottom that I didn't have before, so I need a 6 on the top to cancel it out. In addition, my original problem had a 7 on the bottom, so I need to make sure it still has a 7. So now, this part is going to tend to 1, and 1 times 6 over 7 is just 6 over 7. And this is going to work in general. The limit as x approaches 0 of sine of ax over bx is going to be equal to a over b. Let's do another similar example. This time I have the limit as x approaches 0 of sine of 4x over sine of 9x. Once again, we're going to want to rewrite this. However, I have two signs this time, so I'm going to rewrite two fractions. I need a sine of 4x over 4x, and I also need a sine of 9x and a 9x. So I need some kind of balancing act out front. I have an extra 9 on the top that I didn't have before, so I need a 9 on the bottom to cancel it. I have an extra x on the top that I didn't have before, but I also have an extra x on the bottom, so those will cancel nicely. I have a 4 on the bottom that I didn't have before, so I need to add a 4 to the top to cancel. This is going to tend to 1, and this one is actually 1 over 1 since the fractions is flipped. So 4 over 9 times 1 is just 4 over 9.